Hello everyone and welcome back to my class once again. In the previous video, we discussed how communications are performed in the modern context and the goal to counter noise. Now we will discuss error correcting codes. Before that, though, observe this model once again. This isn't the same one you observed before since there are new concepts in this model. This concept is not added, but is actually an extension of the encoder stage and decoder stage. If you remember, I mentioned that the encoder stage converts the message into binary data and signals. These two concepts are responsible for this process: source coding and channel coding. Source coding is responsible for converting any information to binary data and vice versa, which consists of zeros and ones, something that you mostly see in computer languages. Let's make an example out of it. Consider the following messages encoded below, where north is 00, south is 01, east is 10, and west is 11. Now, what do you think will be the source encoded message if they are set like this? Simple enough. We're just going to convert each of this message into binary data or bits, which is presented here below. So the result will be like this, where 00 is north, 01 is south, 10 is east, and 11 is west. The same goes with the other message set, where southeast is north is like this, and southwest north is like this. For channel coding, this area is responsible for converting binary data into signals and vice versa, which will be transmitted through the channel. Simultaneously, this is also where our error correcting codes perform their roles, since noise occurs in this step. And in this step, we will use parity check as one of the basic error correcting codes used to ensure data transmission between communication nodes is accurate. This is done by adding a single bit to the message, which is known as a redundancy bit. One more thing though, parity check can be used in two different ways, which is odd parity and even parity. Where odd parity is a parity where the number of ones is odd, and even parity where the number of ones is even. Now let's consider the following example. Perform the channel encoding by adding a redundancy bit of size 3. In this case, we are going to use the even parity bit. Now, if you notice about size 3, this simply indicates the number of redundancy bit that will be added in this source encoded words, or what we call code words. And take note that you should use this last number of each code word as a basis for your redundancy bit. So if this is 0, then your answer will be 0, 0, and with additional of 3 zeros. The rest goes the same way, where this will be the answer, where the last number is 0, so 0, 0, 0, last number is 1, 1, 1, 1, 0, 0, 0, 0, and 1, 1, 1, 1, 1. After you get the encoded words, next is the to check if each of the following code words are even or odd. And as you can see, the first two examples are actually even, while the last two examples are odd. This is where noise occurs. This example is disrupted by the noise since they are not actually even. So in order to solve that problem, we're going to change this last bit of each code word to make it even. So in this case, this will become 1, and this one will become 0.